Students, by now you've already taken the first test, and this is the next lecture you need to watch, and it's called Spring13. What we're gonna do in this video is we're gonna try and finish chapter 3 on plate tectonics. Last time we left off talking about there being three kinds of plate boundaries. First one is called a divergent plate boundary, where plates pull apart, move away from one another, and they diverge. And a good example of that might be a mid-ocean ridge, where new sea floor is formed and moves away from the mid-ocean ridge in opposite directions. Second type of plate boundary you need to know about is a convergent plate boundary, where plates push together, such as at a subduction zone, where sometimes the oceanic plate sometimes will sink deeper into the earth at a deep ocean trench. Third type of plate boundary is called a transform plate boundary, where plates slide next to each other. A good example of that would be the San Andreas Fault in California. So, in summary, there's three main kinds of plate boundaries you need to know about: divergent plate boundaries, convergent plate boundaries, and transform plate boundaries. And you can further divide these three main kinds of plate boundaries into 7 different types of plate boundaries. The first is an oceanic continental convergent plate boundary. Second type is an oceanic convergent plate boundary. And the third type is a continental convergent plate boundary. In the first case, oceanic lithosphere pushes up against continental plate. So if an oceanic plate pushes up against continental plate, that's called an oceanic continental convergent plate boundary. If two oceanic plates collide, that's an oceanic convergent plate boundary. If two continents collide, or two continental plates collide, same thing. Two continental plates collide. It's a continental convergent plate boundary, also called a suture zone. Two main kinds of divergent plate boundaries. If you got two oceanic plates moving apart, like at a mid-ocean ridge where seafloor spreads, that's what Hess and Dietz studied, that's called a mid-oceanic ridge divergent plate boundary. But there's another type of divergent plate boundary that occurs on the land, on continents, and we call that a Rift Valley divergent plate boundary. We'll talk about that too. Two main types of transform plate boundaries, where two plates slide next to each other. The first is a land transform plate boundary, such as the San Andreas Fault. It occurs on the land. But we also have transform plate boundaries in the ocean. I'm going to show you the 7 different kinds of plate boundaries. Take good notes, write all these details down. I'm going to show you examples of where they occur around the world, and you need to be able to recognize the 7 types of plate boundaries for the next test. First type of plate boundary we're going to talk about is an oceanic continental convergent plate boundary. So let's talk about that first. Oceanic continental convergent plate boundary. We've talked about it already to some extent. If you have oceanic plate collide with continental plate, the oceanic plate, or lithosphere is going to subduct deeper into the Earth. Why is it that the oceanic lithosphere will subduct deeper in the Earth? Well, remember, the oceanic lithosphere is mafic, and therefore it's more dense, and it will sink underneath the continents. And the place where that occurs is marked by a deep ocean trench. As the oceanic lithosphere subducts deeper into the mantle, it's going to melt because temperatures get higher as you go deeper in the Earth. That's going to make magma, and this magma is going to want to rise, and it's going to make a chain of volcanoes along an edge of a coastline. And the chain of volcanoes that forms at oceanic continental convergent plate boundaries is called a volcanic arc. Where do we find volcanic arcs? Well, wherever we have oceanic continental convergent plate boundaries. I'll give you two examples. Imagine our Pacific Northwest, Oregon and Washington, and so this would be the Pacific Ocean. Oceanic lithosphere subducts underneath Washington and Oregon, forming a chain of volcanoes. Does anybody know what that chain of volcanoes is called? It's named after a dishwashing detergent. It's called the Electrosol Mountains. Now, it's called the Cascade Mountains, and it includes Mount St. Helens, Mount Rainier, Mount Hood, the Three Sisters Peaks. This is a typical oceanic continental convergent plate boundary, such as the one that occurs off the Pacific Northwest to form the Cascade Mountains. Another place where you have subduction of oceanic lithosphere underneath continents is off the west coast of South America. So imagine that this is South America and this is the South Atlantic Ocean. The oceanic lithosphere subducts underneath the continent of South America, forming a chain of volcanoes on the land, and that's called the Andes Mountains, Andes. Those are two top examples of an oceanic continental convergent plate boundary. Next type of plate boundary you need to know about is an oceanic plate boundary, where two oceanic plates collide. Let's see what happens when that happens. When you have an oceanic convergence. Let's see if I can get a bigger picture of this for you. An oceanic plate boundary looks like this. Two oceanic plates collide. They're both mafic, right? Still, one of them is going to be more mafic or have more iron or magnesium. That's the one that's going to subduct. And so here you can see one oceanic plate or lithospheric plate subduct underneath another oceanic plate. And what that's going to do is it's going to produce volcanoes. But these volcanoes are different than the ones we saw previously with the oceanic convergent plate boundary. Instead of having a chain of volcanoes on the land along a coastline, you're going to, with an oceanic convergent plate boundary, you're going to form a chain of volcanic islands. And so you have a mainland, a chain of volcanic islands, and an inland sea. A good example of this would be the islands of Japan. Let's take a look at the islands of Japan, which form an oceanic convergent plate boundary. Here you can see the four main islands of Japan: Hokkaido, Honshu, Shikoku, and Kyushu. They're formed at an oceanic convergent plate boundary. Here you have an inland sea as well, called the Sea of Japan. Another place where we have an oceanic convergent plate boundary is the Philippines, where you have the Philippine Islands mainland Asia and the Philippine Sea. Another example is the Aleutian Islands in Alaska, where you have Alaska, the mainland, and then you have the Aleutian Islands, and then you have an inland sea. Those are formed at Oceanic Convergent plate boundaries. The long and short of it is, at Oceanic Convergent plate boundaries, you form island arcs like the Philippines, Japan, and the Aleutian Islands. Next type of plate boundary we want to talk about is a Continental Convergent plate boundary. And that occurs when two continents collide, such as India. Beautiful country. India. Let's take a look at why India is a good example of a continental convergent plate boundary. In order to understand that, let's take a look at India 55 million years ago. India was an island, and it moved north. And here is India 38 million years ago. 10 million years ago, India collided with mainland Asia, and so the two continental plates met, India and mainland Asia. Both are felsic. Felsic rocks cannot be subducted. So when two continental plates collide, it's like two freight trains colliding together. The only way to go is up. And when you form this mountain range at these continental convergent plate boundaries, those two formerly separate continents are sutured together, like a physician suturing together a wound. And this place where they're sutured together, you form a mountain range. And for India, it was the mountain range, the Himalayas. The Himalaya mountains are from the suturing together of India and mainland Asia. Now, give you another example of a suture zone. Let's take a look at the biggest country in the world. What's the biggest country in the world? You know that. Russia. And let's take a look at the Ural Mountains. Okay, let's do some basic geography here. This is Russia, the largest country in the world. Here's the Ural Mountains. Everything west of the Ural Mountains is considered to be Europe. Everything east of the Ural Mountains is considered to be Asia. And this large continent we call Eurasia, which includes Europe and Asia. Well, Europe and Asia were not always connected together. When Europe and Asia collided together, they were sutured together right here at the Ural Mountains to form a new continent called the Eurasia. That's another good example of a convergent plate boundary, where two formerly separate continents were sutured together. Now let's take a look at Pangaea, for example. Pangaea was one continent, right, in the past. But now let's go further back. Pangaea formed 245 million years ago. Mark that number in your head. That's 245 million years ago is when Pangaea formed. Well, in the past, let me see if I can get a picture of before Pangaea. Okay, so in the past, um, here's a nice picture here, and we're going to be talking a lot more about this later on, but this is the Earth's surface with all the different continents, 545 million years ago to 500 million years ago to 450 million years ago. You can see all these separate continents came together to form Pangaea. When those continents came together, they were sutured together. So that's how continents grow, when you have continental convergent plate boundaries. Two types of divergent plate boundaries you need to know about. Two types of divergent plate boundaries, the mid-ocean ridge and the Rift Valley. We've already talked about mid-ocean ridges in great detail. Mid-ocean ridge is where two plates move apart. That's what Hess and Dietz talked about, right? Where two oceanic plates move apart and magma rises to form new sea floor. That's one type of divergent plate boundary where new sea floor is formed. But we haven't talked about the other type of divergent plate boundary that occurs on the land, which is called a Rift Valley. How's that work? Well, let's take a look. Best place to see a Rift Valley is in one of the most beautiful parts of the world called East Africa. And we'll talk a lot about East Africa later on because that's the birthplace of mankind. That's where humans began. But you can see in Northeast Africa that the rocks are being pulled apart. So this is a divergent plate boundary that occurs on the land. And when that occurs, you can see all the water here. Sea water is flooding into this area. So this part of Africa here in Ethiopia is going to break off away from Mother Africa, and the ocean is already flooding in here. This part will become an island and separate from Africa. That's how continents break apart. They break apart at rift valleys. To see that more clear, take a look at this picture here. Here's Saudi Arabia. Here's Africa. What body of water is between Africa and Saudi Arabia? Moses parted the Red Sea. Yeah, so the Red Sea divides Saudi Arabia from Africa. It was formed at a divergent plate boundary, so that the Arabian plate is moving towards the northeast away from Africa, and seawater has flooded in the area in between. Saudi Arabia is part of Africa. You might not think of it as being part of Africa, but it is. It's simply that it has broken apart from Africa due to a divergent plate boundary that occurs right here in the Red Sea. And that's how continents break apart. The Gulf of Aden, same thing. It broke apart from mainland Africa. So there's another divergent plate boundary there. So continents break apart at rift valleys, a type of divergent plate boundary. Continents come together at continental convergent plate boundaries, also called suture zones. Transform plate boundaries occur where plates slide next to each other. And we already talked about the San Andreas Fault being a good example of a transform plate boundary. Most of you are not from California, so let's take a look at the geology of California a little bit. Here's the San Andreas Fault going all the way from northern California off of a little town called Eureka, California, the birthplace of President Reagan. And it goes all the way down here to the southeastern part of California. And this is a transform plate boundary. This plate here to the west of the San Andreas Fault is called the Pacific Plate. This plate over everything to the east of the San Andreas Fault is the North American Plate. every time there's an earthquake, the Pacific plate moves towards the northwest, and the North American plate moves to the southeast. Think about it. San Francisco and Oakland are to the east of the San Andreas Fault, and San Diego and Los Angeles are to the west of the San Andreas Fault. So every time you get an earthquake, Los Angeles moves closer to San Francisco, doesn't it? Because this plate's going to move this way, this plate's going to move that way. After millions of years, Los Angeles and San Francisco are going to be right next to each other. Here, once again, is a map of California showing Nevada and Oregon also. This is all the North American plate over here to the east of the San Andreas Fault, and this is all the Pacific plate to the west of the San Andreas Fault. So let's take a look at the bigger picture here. Almost all of the United States is on the North American plate here, as you can see. Everything from Alaska, even parts of Russia, to Tennessee, to almost all of the United States. Oliver Springs, everything is on the North American plate. Greenland. But there's a small part of the United States that's on the Pacific plate, and that's Hawaii and Southern California. Here you can see the transform plate boundary of the San Andreas Fault right here. Another type of transform plate boundary is a transform plate boundary that occurs in the ocean. Let's take a look at transform plate boundaries that occur in the ocean. And what these transform plate boundaries do, I'm going to try, is they cut across the mid-ocean ridges. So here you can see the mid-ocean ridge, which is a divergent plate boundary, where new seafloor is being formed, but it's cut by these transform plate boundaries. This part here has moved this way to the east. This part here has moved this way to the west. This plate here is moved towards the east. So these transform plate boundaries can actually cut the divergent plate boundaries, cut the mid-ocean ridges, and those are another type of transform plate boundary that occurs in the ocean. Here you can see the mid-ocean ridge, the mid-Atlantic ridge in the Atlantic Ocean, and note these black rocks here. They're mafic, aren't they? Because they're black in color. They're small crystals, so they're aphanitic, they're volcanic, and they cooled quickly. So this is, you can actually see these on the bottom of the sea floor. And these are called pillow basalts. A pillow, like a pillow you sleep on. They kind of look like a pillow. And these pillow basalts, not sleeps, but pillow basalts, are found at the mid-ocean ridges. That's the new sea floor that's erupting. It's erupting onto the sea floor, and it cools because as that lava comes into contact with the cold seawater, it cools to form these pillow-like shapes. That's the new sea floor that's formed at these mid-ocean ridges. Again, here you can see a bunch of rift valleys. Here's one here forming the Red Sea, another one forming the Gulf of Aden. Another rift valley here as this part of Africa continues to break away from mainland Africa. Continents come together at continental convergent plate boundaries, also known as suture zones, and they break apart at rift valleys. So Pangaea broke apart along a whole bunch of rift valleys, so that Africa broke away from North America, so that Europe broke away from North America, such as Antarctica breaking away from Australia. They all occur along rift valleys as continents are pulled apart. When you think of Japan, think of a oceanic, continental, oceanic. I'm sorry. When you think of Japan, think of an oceanic, convergent plate boundary. That's quite a tongue twister. Like Peter Piper picked a peck of pickled peppers. You know, oceanic, convergent boundary forms chains of volcanic islands, like the islands of Japan. Another thing you want to think about is when you see these oceanic, continental, convergent plate boundaries, don't forget oceanic lithosphere subducts underneath the continental lithosphere, forming a volcanic arc, a chain of volcanoes along the edge of a coastline, such as the Cascade Mountains or the Andes. And these are always marked by these black triangles that show the subduction zone. And there's a deep ocean trench right here marking the subduction. And here you can see the Andes Mountains formed at a oceanic continental convergent plate boundary. When you think of a continental convergent plate boundary, think of India colliding with mainland Asia, forming the Himalayan mountains. When two continental plates collide, there's no subduction. Instead, it's a collision, like two freight trains coming together, forming a mountain. This mountain range glues together those two formerly separate land masses. If you think about it, we have the Atlantic Ocean today, the Pacific Ocean, the Indian Ocean, and the Arctic Ocean, right? But in the past, we have ancient oceans that no longer exist. For example, what happened to the oceans that existed before Pangea? Well, we know they were there. How do we know they were there even though those oceans don't exist? Because those ancient oceans are preserved in these rock sequences called ophiolites. And there should not be an O there. Ophiolites. Ophiolites are these sections of rock that preserve ancient oceans. So we can study ancient oceans by looking at ophiolites. How do we know that these sequences of rock represent ancient oceans? We know that because of the principle of uniformitarianism. The present is the key to the past. If we want to find remnants of ancient oceans preserved in rocks, we simply need to look at modern oceans and see what types of rocks are formed there. And then we can find those same types of rocks and find ancient oceans. If you look at modern oceans, what do you have? You have sedimentary rocks on top, such as chert and flint in the deep ocean, or in the shallow ocean, you're going to form chalk and limestones. Beneath that, you're going to have basalts. Beneath that, you're going to have gabbro. And beneath that, in the mantle, you're going to have peridotite. Well, if you find the same sequence of rocks and they existed before Pangea, they existed before 245 million years ago, then you're actually looking at ancient oceans in these sequences of rocks called ophiolites. Here you can see the mid-ocean ridge system. Here's a mid-ocean ridge here, but the mountain range is cut by these transform faults. Here you can see the subduction zone. And this is an oceanic continental convergent plate boundary right here. And you form a volcanic arc, such as the Cascades or the Andes. The Appalachians were also formed at an ancient oceanic continental convergent plate boundary, too. Here you can see our Pacific Northwest. Canada up here, the province of British Columbia with Vancouver, Washington, Oregon, California, and this is the Baja Peninsula. This is mainland Mexico. This is the Gulf of California. Here's the San Andreas Fault, dividing the North American plate from the Pacific plate. You can see that the Pacific plate moves to this way to the northwest with every earthquake, and this part the North American plate moves to the southeast with every earthquake. So that with every earthquake, Los Angeles moves closer to San Francisco since they're on the opposite sides of the San Andreas Fault. Here you can see a subduction zone as this tiny little plate called the Juan de Fuca plate subducts underneath Oregon, Washington, and British Columbia, producing a chain of volcanoes, a volcanic arc, which we call the Cascade Mountains. Here you can see the situation off the west coast of North America and South America. Here's the Pacific plate. Here's a small Nazca plate and the Cocos plate. And the Pacific plate's all of this. This is the North American plate here. Notice that we have subduction occurring all along the west coast of South America and the west coast of Central America, producing volcanoes, the Andes Mountains, and beautiful volcanoes, Costa Rica and southern Mexico. Transform plate boundary here between this part of Mexico and going all the way up here to Eureka, California. And we have a subduction zone here where Pacific plate subducts underneath the North American plate produced over here. And so we got another thing here. What they're trying to show you is these dots here are copper deposits. And in geology, a lot of the jobs are involved in mining. So we need to mine to make all of our products, right? From computers to cell phones to household goods. Everything is, where do we get the raw materials to manufacture products? Most of it comes from minerals. And minerals that can be mined for a profit, we have a special name for that. They're called ores. So an ore is a mineral that can be mined for a profit. And one of the minerals that we mine for a profit is copper. Silver and gold are also ores. So are gemstones like diamonds and emeralds and opals. So geology, we want to translate what we know about the earth to produce jobs for the economy. And one of the ways we can do that is by finding ores. One of the most important ores is copper, which is used for plumbing and also for soldering in electronic devices. You can see that these copper deposits, these copper ores, are found here near the subduction zone. Why do precious metals, especially and gemstones, form at convergent plate boundaries? It's important to know that. Well, because at convergent plate boundaries, subduction occurs in most cases, unless it's a suture zone. So that as oceanic lithosphere subducts into the earth, it melts, producing magma. The magma rises, comes into contact with the groundwater, and heats it up. These super hot fluids concentrate elements in them, such as gold and silver and copper, producing ore deposits. And gemstones are also formed by hot water, as elements are concentrated to form beautiful crystals of diamonds, emeralds, rubies, sapphires, etc. So, another reason to be interested in plate tectonics is to find gold and silver and uranium and all of the valuable mineral resources that we need to extract from the earth and gemstones. So don't you think it would be interesting to mining companies to find out where the ancient convergent plate boundaries are so that they can know where to find diamonds and gold and silver and platinum and all the things we need? Yes, and that's why we do that in geology. We try to find ancient convergent plate boundaries. Next thing I want to talk about is mantle convection. And here you can see a picture showing why does plate tectonics occur? We have to ask ourselves the question as to why we have plate tectonics? Well, the original reason why people rejected Wegener's idea of continental drift was the simple fact of the matter that he could not explain what was driving the continents to move, right? What caused the continents to move? We learned what caused the continents to move partially by seafloor spreading and partially through Tuzo-Wilson. But in the 1980s and after, scientists have come to the realization that mantle convection drives plate movement. What is convection, first of all? Well, convection is a way to move heat around in the earth. What is heat? Heat, according to physicists and chemists, is a type of energy that causes matter to either increase in temperature or to change phase. In other words, if you add heat to a material, the temperature of the material will go up or its phase will change, such as when you heat ice, it's going to change into liquid water. And when you add more heat to liquid water, it's going to change into water vapor. So heat can cause materials to increase in temperature or to change phase. Well, when you heat rocks in the mantle, they undergo convection. And what is convection? It's a method by which heat moves through materials. Imagine for a moment waking up in the morning and you put a pot on your stove. Doesn't matter if it's electric or gas. You pour water into the pot. And imagine that the pot is Pyrex, so you can see through the pot. And you want to make oatmeal. Well, what do? First, you heat up the water, right? Then when you add the oatmeal flakes into the water and you watch the oatmeal flakes, they swirl, right? That's showing how the heat is making your oatmeal swirl. Your beef stew, when you make that, it's going to swirl. And the same thing happens in the mantle, is that underneath the mid-ocean ridges or rift valleys, magma is going to rise. And in the mid-ocean ridges, we form new sea floor there. And then as this hot material gets closer to the surface, it gets closer to colder rocks and to cold water, like in the oceans. And so it's going to start to sink back down. And it sinks back down at the subduction zones. And it rises again at the mid-ocean ridges. So it's a continuous cycle. So mantle convection is what drives the movement of plates. But where does the heat come from to cause this mantle convection to occur? That's radioactive isotope decay. Radioactive isotope decay causes mantle convection. And that's when one isotope changes into another isotope. Like we talked about earlier, carbon-14 changing into nitrogen-14, or uranium changing into thorium, or radium changing into radon. When one isotope changes into another, radioactive energy is released. We have lots of radioactive isotopes in the mantle, and that drives these mantle convection cells, which drive plate tectonics. Here's a stew. You can see in your stew, the carrots and the potatoes and the celery and the beef cubes are going to swirl because of convection as heat is added. Another thing that plate tectonics does is it affects the distribution of life on our planet. And in the next video, we'll go more into that. So I'll probably make one more video here, or maybe not. We'll see. It might be next week. We'll see. Anyway, yeah, I'll make one more short video, and then that'll be it for this week.